Okay, welcome back to week 2 of EL164 Basic PLCs. Again, I'm Patrick Van Ottern here to teach you guys the basics of PLCs. Okay, so we are going to be talking about number systems and codes, learning things like binary and hexadecimal and how they're used in a PLC format. We're going to start with the decimal system. The decimal system is a system that most everybody uses on a regular basis and are very familiar with. This is what they call a 10-based system. Of course, everyone knows you start with 0 to 9, and then you go 10 to 99, and then 100 to 999, and then 1000, and continue onward. That's considered the 10-base system. You will also hear that term called a radix. The 10 as being called a radix. That is in this section as well. You'll be learning about this. So here in a 10-base system, here's the radix, as I mentioned earlier. If you're following along here on this piece here, I'm going to pull up the laser pointer. The radix here, or base of a number. So again, the decimal is based on a value of 10. And then here, if you follow this format, each decimal has a certain weighted value to it. Starting at the very right is the least significant, or LSB. It'll also be called least significant bit, or least significant digit here. And to the left is the most significant bit, or the MSB, most significant bit. So here, as you can see, if you go through and place a value of 0, 1, 2, and 3 in each one of these digit locations, and you multiply the value in each one of those locations by 10 to that 0, you come up with a value of 1962. So, giving a weight to each one of those digits. Binary system works on the very same principle, only difference is instead of 0 to 9, we go what? 0 and 1. So let's take a look at how that works. So a binary system is based either on or off, or high and a low. So it's on, typically it's high. If it's off, it's typically low. There is some scenarios where that's a little flip-flop, where they use a low signal to indicate as it being on. But for the most part, you're going to be using a 1 for on and a 0 for off. So here, as you can see here, as the binary system is used, you're using a series of ones and zeros to represent a value that we would understand. So the decimal value we do understand. So by comparing the decimal value to the binary value, it gives you a pretty good understanding of how binary is using a series of ones and zeros to develop the same numerical values that we're familiar with in a, say for instance, a 10. It was a 1, 0, 1, 0. And all number systems start at 0. So here we are. We're looking at this this chart of different components, different numbering systems. Notice that decimal, octal is a numbering system that uses 0 to 8, or 0 to 7, I guess would be more accurate. And hexadecimal is something that we typically use in binary. Octal was used when I first got into this business. It was a pretty big deal. Because a lot of systems were based off of 8-bit technology. 8-bit is kind of gone to the wayside. Not too many companies even consider octal anymore. I can't think of too many applications that use octal. So we're not going to spend any real time on it. I'm just going to make you aware of it. It uses a 0 through 7 base value of 8 and a radix of 8, and that's about as far as I'm going to take that. So you can find more information in the book on that and or online, but we're gonna focus mostly on decimal, binary, and hexadecimal. Noting that of course the decimal is base 10, binary is base 2, and hexadecimal is base 16. Breaking into hexadecimal a little bit, the hexadecimal is based off 16 digits. As you can see here, it starts with 0, as they all do, and it ends in F. The reason they set it up so it's A, B, C, D, E, and F, and not 10, 11, 12, 13, is because when you're dealing in numeric values in a processor, you do not want it to take more digits to represent the same thing. So at that point, they decided to go to a decimal value, or a numeric value, excuse me. So an A represents the same thing as a 10, B would represent 11, C would be 12, D 13, E a 14, and F a 15. So that is is how hexadecimal is represented, 0 to 15 or 16 bits of information. Keeping in mind, you do have to count 0 as a decimal placeholder. So that makes it for 16 bits, or 16 digits. The same thing holds true with 10, 0 to 10, and base 2 with 0 and 1. So converting a binary number to a decimal number. Now, noting here, we take a series of placement. Starting at 0, we come in 0, 1, 2, 3, 4, all from starting at the right, going to the left, indicating this 1 as being what? The least significant bit, the LSB, and the 7 here, or this 1 in this location, as the MSB, or most significant bit. So it is here where we take the information from each one of these locations and multiply it to the value of 2 to that power. So here I've got a 1, it'd be 1 times 2 to the 0, where 2 to the 0 equals 1, and 1 times 1 equals 1. So that puts a value of 1 in that first location. The very next location, as you can see here, is equal to 0. So 0 times anything, of course, is going to be 0. 2 to the first power is 2, so 0 times 2 equals 0. The next position here I have available is the third location, 0, 1, and 2. So this would be 2 to the 2 power times by 1. So 2 squared, of course, is what? 4. 4 times 1 is 4. And right on down the line. So as you can see, I won't waste any more of your time with that. Oh, at the very bottom, what we do when we come up with all these values, we got to add all these up to come up with the decimal equivalent to that number. And that's how that is done. So here's how we define a word. We'll have a lower byte, an upper byte, and a word. Typically nowadays, all of our processors will have a 32-bit word instead of a 16-bit word. We'll still have a lower byte and an upper byte, but and typically a byte is 8 bits. So what we would have is still we have 8 bits of information, but we would have say 2 lower bytes and 2 upper bytes, or possibly as many as that. So it depends on who lays it out and what machine is, but you kind of get the idea from this layout how that is done. So LSB, MSB over here. That's always LSB on the right, MSB on the left. Most significant bit. Okay, so here's how the PLC organizes its memory. We're using bytes, single words, or double words. A double word, of course, nowadays is considered to be a regular word in the standard format is going to be 32 bits long. So when we're dealing with most of our word applications will now be in a 32-bit realm. This is some of the technology that the book is going through is 16 bits, just because it's been that way for a lot of years, and the book is a little bit outdated when it comes to that. So as you can see here in the data table, again, reading from right to left, you got the lowest significant bit on the right, the most significant bit on the left. And then the way that it organizes this information is I've got a series of bits of each word, 0 to 15 bits. And then each word has an address location as well. As you can see, here's the word 0, word 1, word 2, word 3. And one word consists of all 16 bits. So you can address a single bit, or you can address the entire word using the address on the left. So if you guys are familiar with a matrix, this very same principle. When you're looking for a bit, you've got to first find the word that you're trying to address. So in this particular case, they've got word 4, and then they got a series of 1s and 0s. So if you were looking for word 4, bit 0 would be a 1, just to give you a kind of an indicator how that works. So converting a decimal number to a binary number, these are a little bit more tricky, not huge, but you can see here, what do you start out with? You start out with the LSB. This gets a lot of people, so make sure when you're doing your conversions, you start out with the LSB, the least significant bit. So your very first division by 2, 47 divided by 2 is 23. It does not divide into it equally, so that means there's a remainder. That remainder ends up over here to the right in our LSB, a remainder of 1. So then you take that value of 23, divide that by 2, and you get a remainder of 1 again. So as you can see, as you continue this process, you have a series of 1s and 0s that end up in this network of numbers. Noting that LSB ends up way over here on the right, and the MSB is over here on the left. This is probably the biggest challenge that students run into is getting these flip-flopped. So if you think of it from this perspective, if you were to take a decimal value and flip-flop the most significant and the least significant bit, that would make a big difference, right? So say you wanted 12 donuts, and you flip the LSB and the MSB on that value, you'd end up with what? 21. So make sure you got the binary numbers correct when you're looking at MSBs and LSBs. Don't get those flip-flopped. So again, here we're looking at some more addressing, another application where they're actually giving us an address. Each one of these words, again, you'll see here, it has an address. So address, I've got word 1, word 2, word 3, word 4, word 5. These are all output words. And then these are all the bits associated with each word, so 0 through 15. So any one of these bits that you wanted to address would be looking something of the fashion of address O:1, and then any one of these bits. So say we wanted a bit 0, it would be O:1/1. Negative numbers. Now that seems a little odd to have a negative number in a binary sequence. Now does it not? Well, the way the PLC operates is it takes that MSB, that most significant bit in a 16-bit or a 32-bit word, and sets that to a 1. Once that is equal to a 1, that value is a negative number. So what that means for us is what? We can't necessarily count all the way up to all 16 bits or all 32 bits. We can only count to a maximum value of the 15 bits, or 31 bits. It'd actually be, if you're looking at it from binary from 0 to 32, it would be 0 to 31, excuse me. So you'd really only have to count, you only really count to 0 to 31. So, but, so if you subtract 1 bit from that, it would be 0 to 30. So anyways, so the most significant bit is the sign value. So if that is a 1, this value becomes a negative. So 2's complement, or 1's complement, they're just showing us some different options that are out there. I am not really too concerned about, I try to focus on things that I have run into in the industry, so I'm going to pass on this one. I'm going to pass on 2's complement as well. We don't really get into too much of that. And I'm going to pass on the octal system because we do not really work too much with that. So as you can see here, octal goes 0 through 7, and then 1 through 7, 10 through 17, 20 through 27. That's just a silly numbering system that nobody uses anymore. So I don't see a value in it. So I'm going to jump through that. The hexadecimal system, by the way, is probably the most utilized when it comes to PLCs, working with PLCs. So this one I find to be very important, and so we will be spending some time on that. So we're going to go through this a little more. So letters A through F, of course, represent numbers 10 through 15. They're able to do that because what? They only use one character. They don't require 2 characters, so they have 1 character to represent 0 through 15. So whether it be a 0 or an A or an F, it still represents the same information. One of the patterns that you'll see here is that the decimal value, of course, aligns quite well with the hexadecimal. Just the 10, 11, 12, just the last pieces are a little bit different. Also, the binary sequencing you'll see here is pretty easy to follow a pattern there. If you really look closely, you'll see if you ever need to know a binary sequence and you don't remember what bit was on when you had 1 character, this is a real easy way to do it. You go first line, you go 0, 1, 0, 1, 0, 1, all the way down to the bottom. You make 15 of those. And you come over in that 1 slot here, you got 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, all the way down to 15. Come to the 3rd character, you go 1, 2, 3, 4 zeros, 1, 2, 3, 4 ones, 1, 2, 3, 4 zeros, 1, 2, 3, 4 ones. And then that last column is 8 zeros and 8 ones. What that does is gives you this pattern, and you can align it with either decimal and or the hexadecimal. And it gives you a pretty good way to come up with a system to convert from hexadecimal to binary and or decimal. Here is the correct way to do it. Now, this is the converting hexadecimal to decimal. Okay, so this time, remember, we got that radix or that base value of 16. Here they fail to give us that 0, 1, 2, but we do know that because they multiply by 0, 1, 2, that is truly the case. So the very first case is we have a 7 times 16 to the 0 power. 16 to the 0 power is 1. So 7 times 1 equals 7. B, we know as 11. 11 times 16 to the 1 power is 16. So 11 times 16 is 176. And then the third one is actually the 0, 1, 2, which is the 2 power. So 16 to the 2 power is 256 times 1, because the 1 value of here comes up with 256. We add these guys together, and this is the value of the decimal number. So converting decimal to hexadecimal. This is actually pretty little. This is a kind of a cool little system. So basically, think of each digit as 4 bits of information. So if you look at here, you've got a 1. So a binary 1 is 0, 0, 0, 1. And if you do that chart like I showed you before, that'll help you make this transition. But if you flip back to the previous slide as well, you can see that 1, 0, 1, 1 is truly a B in hexadecimal. And then the last piece is a 0, 1, 1, 1, which is a 7 in binary. So it's essentially each one of these digits represents 4 bits in binary. The BCD, or binary coded decimal system. Here's another system that's kind of outdated a little bit. It's used a little bit here and there, but most applications that you will run into today to convert information or send information to another system or process, it's all done through Ethernet. So they're sending true values, not necessarily a binary coded decimal. It works the same, uses kind of the same principles as hex. The only difference is it doesn't have the A, B, C, D, E, F. It just uses 0 through 9. So if you follow along here, you will see BCD and binary are very, very close here, right? So we got BCD, hexadecimal, and decimal are all, fairly close together. So we got, so when you send a 0, a 1, a 2, a 3, it's and BCD and binary are coming right along here, right? The same, and same, right along the same lines. Where it gets different is that, like I mentioned before, is BCD does not use the A, B, C, D, E. They go to the next level over. So when you get a 1, 0, it puts a 1 in this value and a 0 in this place. This is a 1, 1, 1, 2, 1, 3, 1, 4. So it's not used excessively. I just need you to be aware of it. And because there is some displays, some older displays that still use BCD, even some of your touch screens from older versions may actually display in BCD. So you do need to be aware of it. So again, breaking it down into smaller pieces. So 3, if you follow your binary sequencing, you'll see it's a 1, 1. A 6 is a 1, 1, 0. An 8 is a 1, 0, 0, 0, and a 7 is a 0, 1, 1, 1. So then they're going to get into some more high-end here. Decimal 49 expressed in binary is this. And then the same number expressed in BCD is this here. So they're showing us an application where you'd have like a thumb switch that would actually be feeding some input information to an input module. Again, there may be an older application out there that actually is using some of this technology, but quite often nowadays you don't really run into this too often. There's a few applications out there, but not very many. So they're showing us here how this numbering or this thumb wheel switch is addressing the inputs on the PC. So here we got double-digit thumb wheel switch simulation. So they're doing the same thing, only adding another digit to it. So you can see here. You can follow the binary sequencing as fast as they're flipping through it. It's kind of fast though. So again, thumb wheel to read out, you got there's a command we'll be getting into a little bit to tell you how some of the conversion goes, but the idea is just to get you an idea of the BCD is out there. It's not something that we're going to get real in depth in. It's going to be kind of a brief discussion of it. Something to be aware of. Okay, so the radix, again, we talked about, you're able to change to different formats, and all the newer PLCs allow this as well, so you can switch it to display binary, decimal, hex. So it's pretty handy to be able to flip back and forth. It gives you a means for converting from one memory system to another, so you can, if you need to know, like for instance, the number of ones and zeros in a word, this is where hex really shines. And so this is a common experience that I like to share with students is when you're given 16 bits of information, a series of ones and zeros in a word, and you got to translate that information to somebody else. You got to tell them, I've got this bit and that bit on, or this and this on, and this and this and this and this one on, this one off, this one on, this one off. It is a lot more difficult to remember 16 positions than it is to remember 4. So whereas hex can divide all these bits into 4 pieces and be represented by, if I was, for instance, going to acknowledge that this was a hex value, it would be 0, 1, 5, 9. So how I know that is because I've been doing binary for so long. I know all the binary sequence converting, but that gives me, so 0, 5, what did I say, 0, 1, 5, 9. It was easier to remember than a series of zeros. I got to do what it is, 0, 0, 0, 0, 0, 1, 0, 1, 1, 0, 1, 1, 0, 0. You see what I'm saying? Is that it just way easier to manipulate that information using hex than it is all the binary ones and zeros. Binary arithmetic, this is something that the book covers a little bit. It's not something that we use much in the PLC world much anymore. It was something that when, before the technology of the processors really came to be, then there was quite a bit of this. But right now, a lot of this sort of thing is just taking place without a whole lot of effort. So we kind of just skip over this. The same for the next piece of this. They do some comparisons. Here they're talking about data comparisons. This is something that we will be getting into eventually, but they're just talking about some of the basics: equal to, greater than, or less than. Floating point arithmetic as well. We don't really cover that too much, and we're not going to really go through too much of that. You'll see it in the book, but we're going to kind of just float over the top of that. It's just skipping the highlights of that. So this is chapter 3. There'll be a homework assignment associated with this as well, and we'll move on to the next section. Thank you very much, and have a wonderful day.